Welcome. In this session in linear data analysis, we'll explore what we'll call the right transpose product of a matrix. That is, suppose that we have a matrix and it has all real entries with m rows and n columns. And what we'll do is we'll multiply this matrix on the right by its transpose. And let's suppose, for now, that this matrix has linearly independent rows. Previously we considered linearly independent columns. Now we have linearly independent rows. From this statement, I know that A is either square or that it's what we call a short wide matrix, where it has more columns than it has rows. And here it will also be full rank. So now let's form this product matrix and take a look at it. So this matrix, which we'll call B sub U to distinguish it from the B sub V that we had previously, so this is A transpose. And by the spectral theorem, we can write that matrix as some matrix U times some eigenvalue matrix times some matrix U transpose. And the columns of U form an orthonormal basis. Now it will be for the vectors that are all real numbers and have m entries. So that means that I can write this eigenvector basis as U sub 1, U sub 2, and so on, and then I'll now end with the number of rows in the original matrix A, and the eigenvalue diagonals, again ordering it so that they go from largest to smallest. This will be eigenvalue 1, eigenvalue 2, and so on, and then we'll have eigenvalues for as many rows as there are in the original matrix A. Next, let's suppose that the rank of this matrix A is R. Then this symmetric matrix that we formed from A transpose will still be symmetric. Now it'll be positive semi-definite, which means that it will have all positive real all eigenvalues will be real. They'll all be positive. The difference is that now with this matrix, that eventually we're going to hit zero eigenvalues. So its eigenvalue matrix will look like lambda 1, lambda 2, and so on, and then we'll get to the lambda r, which is the last of the non-zeros, and then we'll get zeros for the remaining eigenvalues of the matrix. Let's go through an example, and let's use the same example A as we've used in previous sessions. So that matrix A was 1, minus 1, 1, 1, 1, 1. And now this U version of the symmetric matrix is A times A transpose, and that will be, so this matrix B U will be a 3 by 3 because we have 3 of these. So this will be A transpose times A, so I will get a 2 here, I'll get a 0 here, I'll get a 2 here, oh, I'll get a 0 here, I'll get a 2 here, I'll get a 0 here, and now I can almost fill this in just by the symmetric property, but I'll keep doing my mental calculations that will be a 2, that will be a 0, and that will be a 2. So now I have a symmetric matrix, and it's positive semi-definite. Let's write down the eigenvalues for this. So they're all real, they're all non-negative, but I know from the construction that if A is ranked 2, that BU has to be ranked 2. When I calculate the eigenvalues for this, my calculations are I get eigenvalue 1 is 4, I get eigenvalue 2 is 2, and I get eigenvalue 3 as 0. What are the eigenvectors? Well, they also form an orthonormal basis by the spectral theorem. I can write eigenvector 1 as proportional to 1, 0, 1. So before I continue, let's pause and just do this quick calculation. If I take this and multiply it by this matrix, I get 2, 0, 2, 4, 0, 0, 2, 4. 4, 0, 4, which is a multiple of 4 times this, and we get the correspondence. I find that eigenvector 2 is proportional to 0, 1, 0, and I find that eigenvector 3 is proportional to 1, 0, minus 1. A calculation that you can do is that eigenvector 3 should be in the null space of this matrix. So you can do that cross-check yourself and verify that the null space of B is spanned by this third eigenvector of B.